Hi, this is Lisa Knight, and I am going to go over the Projectile Motion Video Analysis Lab. When you open up the zip file, you will see the video and you will see the start menu or replay box. You'll want to click on start, and basically it's a video of a ball rolling horizontally off a table, and every frame, the location of the ball has been marked. You'll also see a list of data, and you're going to use this data to help you calculate the displacement vectors in the x and y direction and the velocity vectors in the x and y direction. So, for example, at time 0, it hadn't moved at all along the x-axis, and it is 1.08 meters off the floor. At the next frame, it has moved 0.1 meters, and it is still 1.08 meters off the ground because it's moving in a straight line, right? It's not moving at an angle yet. When you get down here to the fourth frame, so this first dot here, when it leaves the table, it is at 0.30 meters and it is at 1.08. And then at the fifth frame, it has now started to fall, right? It's only moved 0.40 to 0.40 meters in the x direction, but now it's 1.06 meters from the floor. And at the sixth dot, it is 0.50 meters along the x-axis, and it has fallen to a position of 0.99 meters. So obviously it's moving at a constant speed in the x direction because it's always moving the same distance. But as it falls and it falls further and further and further, which means it must be accelerating in the y direction. You're going to utilize this information to complete the lab, and you're going to basically be using this data chart. So let's just kind of move this one out of the way, and let's talk about the actual background information. So remember that vectors have x and y components. So we can write those vectors. A vector can be written as a point, right? It can have an x value and a y value. So a displacement vector, the displacement vector r, it can be written as the point rx, comma, ry. And if you are going from one place to another place, you start at one position and you end up at another position, then really that rx is really the change in x between along the x-axis, and delta y is a change in y along the y-axis. Velocity vectors, remember that velocity is the displacement divided by the time. So if I want the velocity x component, I would take the delta x from up here and divide it by the time it took it to move from point 1 to point 2 on the x-axis. And then to find the Vy component, I would take the y displacement vector and divide it by the same time. Remember that when we find a change in anything, it's always the final minus the initial. So we want to start at the first point and go to the second point. The second point minus the first point would give you the change. If I'm asked to draw a vector component, so this if you look here, this vector at an angle here is pointing down. So it has a y component that starts at the top of it and points straight downward. So if you're asked to draw vector components, I expect you to draw that component as an arrow pointing down, and it will stop where the vector stops, right? You don't want to go any further, and you don't want to be too short. It needs to be a vector, and then you need to label it delta y. And then the x component would start here, so its start is at the tip of the y, and it would go across to the right, and it would stop at the tip of the vector, and I would label that delta x. So you want to make sure that your vectors make a right triangle, and that you draw them tip to tail, and that you definitely show the direction by drawing them as arrows, not lines. A line segment is not a vector. A vector is an arrow. So one thing you'll have to do is you'll have to, you're going to be asked to draw the displacement vectors on a diagram, on the dot diagram of the motion of the ball. So how do we even figure out the displacement vectors? Well, remember that in the x direction, the change in x is the final minus the initial. So we can't really make any measurements here, right? But at the second point, we can start find the change, right? Remember, change is final minus initial. Well, we started out at 0 and we went to 0.1. So final minus initial would be 0.1 minus 0. And so the change in x from the first point to the second point is 0.10 meters. And then for the third point, it's 0.20 minus 0.10, which is also a change of 0.10 meters. And actually, if I keep doing that down, the next change will be 0.3 minus 0.2, which is 0.10, 0.4 minus 0.3, which is 0.10, and so forth. So in my change of x's are always going to be the same. And I didn't complete the chart, but you guys will do that. So all of my delta x vectors for each point should be drawn to represent 0.10 meters. And that's really just the distance along the x-axis between each frame of the video. Now, in the y direction, for the longest time, there is no change in y, right? It just stays rolling along the table. But after it gets to the fifth point, it has dropped 0.02 meters. So the change in y would be 1.06 minus 1.08, which is a negative change, right? So that means that my arrow should be pointing down and it should represent 0.02 meters in length. And then the next one, for example, will be 0.99 minus 0.106, and that change will be a little bit more. It'll be a negative still because it's pointing down 0.07 meters. So how do I actually draw these? Well, I know that all the x components for each dot here are always going to be the exact same length. They are going to be the distance between the points, right? Because this object is traveling at a constant speed forward, which means that it's always traveling the same distance, and you have calculated that distance to be 0.10 meters. So I am going to insert and draw an arrow here to represent my Vx, right? From the first point, it starts at the point and it ends at the next point. I should draw vectors that are exactly the same length for each point, representing delta x. All the delta x's will be exactly the same point. So if I do this for the fifth dot here, I will have a vector pointing in the x direction at that dot that looks exactly the same as all the others because they all represent 0.10 meters. So if I wanted to draw another, if I wanted to draw another one, that's my bad. Then I would just put it right here. Let's make it look a little bit better. Okay. I would put it right there, and so forth. So each dot will have an x vector going the same direction. So now let's look at what's going on in the y direction. So between the fourth and the fifth point, it drops 0.2 meters. Well, how long should that vector be? I know it should be pointing down. And where should it be, right? It's going to start, it's got to be pointing from the first point to the second point in the calculation. And so this went from point, so it's got to start at point, the vector has to start on the fourth dot. And it has to point towards, in the right direction, to represent that length of 0.02. The direction is given by this negative, right? It's got to point down. It's going to fall down. It's going to fall down 0.02 meters. So the way that I represent that here is I go to the 1, 2, the third point, that's the point right where it's going. And you notice how the third point, you see how the next point is just a little ways down? It's just a hair down from where it would have been if there was no gravity, right? It would have just kept going straight along this path. But there's gravity pulling on it, and it's pulled on it for just a little bit of time. So what I'm going to do is this. I'm going to take my arrow and I'm going to start at the third point, and I am going to draw it just as long as that length right there. So there's my VY. When I draw my next length, I'm going to start at the next dot and I'm going to draw, oops, that's my bad. I'm going to draw this one. It's going to start at the fourth point and it's going to go all the way down until it's level with the fifth point. Okay, so this length would represent negative 0.07 meters. And then the next one, I'm going to do the same thing. I'm going to start on the sixth point and I am going to draw it down straight so that it's level with the seventh point. And so you notice that's what's going to happen is you're going to have a series of vectors that represent in the x direction it's moving forward the same speed. So the vectors in the x direction should all be the same distance, but the velocity of the y vectors should be moving down. Then I'm going to now I'm doing this in Word, in PowerPoint, but you guys are going to do this by hand, right? You're going to sketch this in by hand. What am I going to look for? I'm going to look for the fact that you're showing the magnitude of the vectors in the x and the y direction so that it makes sense. And I want to see the values of these. So this is 0.10, 0.10, 0.10, 0.10, and then Vy is negative 0.02. This Vx would be 0.10 meters and Vy would be negative 0.07. So I'd like to see those labeled, please. And so I want you to label them so that I know that you know how big they are, what these links are representing. And you're going to do that for each point. And you're going to do that for the displacement. Then when it comes time to do the velocity vectors, how would you do that? Well, the biggest difference is that you need to know the time interval, right? So the velocity in the x direction is going to be equal to the change in x all over the change in time. So you're going to have to look at your data chart and figure out how much time lapsed between the first point and the second point, and you're going to divide the 0.10 by that time. Now, it should be the same difference in time, right? Because the frame rate is 1/15 of a second, or 0.067 seconds. So in this case, I'm going to find my Vx, I'm going to take my delta x and I'm going to change it by the change in time for, between each successive point. So if I do that, and let me just type this out for you so you can see it. Delta, my bad, delta time. So this is going to be 0.10 divided by, and if I look at my chart here, it went from 1 to 2, the time difference is 0.067. And actually this is going up by 0.067 every instant in time. Okay, so I'm just going to utilize 0.67 for that. Okay, oops. I'll put that in my calculator, and we want to give it 2 significant digits when we round it so we don't lose our precision. So if I do that in my calculator, I'm going to get 0.1 divided by 0.067, and I'm getting 1.49 or 1.5 meters per second. So it's moving forward at 1.5 meters per second. That's going to be the same in the x direction, right? Because it always goes the same distance. When I draw that vector, I'm going to draw my vectors exactly the same way I drew them before on the diagram, but I'm going to label it with the appropriate values. To find my my velocity in the y direction, I am simply going to do the exact same thing, but with the y component. So, for example, from point 3 to point 4, that's going to be negative 0.02 divided by 0.067. So let's do that. 0.02 oh, my computer, it just died on me. Sorry, guys. All right, here we go. So 0.02 divided by 0.067 is, and let me do that one more time just to make sure I didn't do anything wrong. Excuse me, negative 0.30. I'll round it to 2 sig digs. Negative 0.30 meters per second. And I'm going to go through and take all my delta y's and divide it by 0.067. Sorry about that. Coughing. Then when I go and I draw my diagram the exact same way that I've been drawing the diagrams. Okay, diagram's going to look exactly the same for velocities, but the difference is when I label these, it's going to be labeled with the velocity values in the x and the y direction for each point. And if you have any questions, please let me know.